Welcome to the next lecture on PCM transmitter and receiver. In the previous session, we have drawn the block diagram of a PCM transmitter and a receiver. In this session, we'll explain what is PCM transmitter and how it works, the principle of reception in pulse code modulation, and so on. So the first block in the block diagram of PCM transmitter is an anti-aliasing filter which removes the high frequency components of that signal. Okay, this is called as anti-aliasing filter because we will be having aliasing effect. We have seen what is aliasing effect in the previous lecture. So we are avoiding this aliasing. We are using an anti-aliasing filter, and we will not have, see, all frequency filters, even though it is band limited, we cannot have a sharp cutoff always. We'll have a curve, and this curve might vary according to the conditions. Okay, so before sampling, what happens is that the input signal or the message signal is passed through an anti-aliasing filter by removing the high frequency components. Okay, after that the sampled signals are quantized, like what we have seen about quantization in the previous classes. It is kept quantized, uniformly spaced, and so that we'll have a sufficient, or we can have enough signal to noise ratio that can be easily reconstructed in the receiver end. So the explanation for the first block, anti-aliasing filter. Then what happens? So the quantized signals are binary encoded and fed into the channel for transmission. Okay, after the signals are quantized, these quantized signals are fed into the channel so that it is transmitted. We have regenerative circuits in between, right? What are the three components of regenerative circuits? Equalizer, timing circuitry, and third one, decision making circuit, right? So what it does, it eliminates the channel noise, and not eliminates, in fact it reduces the channel noise and is fed into the receiver. Okay, the reconstruction filter, decoded and then given into the reconstruction filter. So I believe that all of you are very clear with how a PCM signal is generated and transmitted and received. Is there any clarification regarding PCM transmission reception system? Anybody? This is a very common question that appears in your university exams. You may be asked to explain PCM transmission and reception with neat block diagrams. Is that clear? Next, what we have seen, we'll be seeing in some more in depth about quantization levels, quantization zones, and quantization errors. So if we have L quantization levels, we have each value divided between 0 to L minus 1. Because we have L quantization now. From 0, if you're starting, you'll have L minus 1 levels. Okay, each sample you select, you will be having, sometimes the sample will be between these levels. So you need to have a decision to make whether this is 0 or 1 or whatever it is. So that will be approximating it into a midpoint. So we'll be assuming in such a way that we have all sampled points, as many as possible, a quantized digital value. Is that so? That is what is shown here. You have a continuous sample M, you have a quantizer with a transfer function G when we have discrete samples of V. So you have possibilities of sampled points in between two values. In that case, we make use of the decision circuitry or the threshold values to finalize on which level it has to fall. So quantization zones. As I previously told you, I've designed slides in such a way that each and every slide would be an answer to a question. So that's the reason why some of the slides are repeated. This is an example of how we are going to quantize signals. Let us take, for example, the minimum value is -20 and the maximum value is +20. And we are dividing this into 8 equal quantization levels. If it is uniform quantization, the step size delta is given by 20 minus 20 by 8. That means 40 by 8, 5. So you have step size to be 5. So we have 8 zones. You take it as, if you have step size to be 5, we'll be naturally having 8, right? 8 zones, one from -20 to 15, and -15 to 10, and so on. And then we'll take its midpoints where we'll have 8 values from -17.5 to +17.5. These are the midpoints of the quantization zones. And I've included all these things because your university, there was a question about explaining the quantization in terms of examples. They might even give you values and they may ask you to do, instead of -20 and 20, they may give their own values. They'll give you the quantization levels also. You need to find out the midpoints and assign the necessary codes and zones to it. Is that clear? All of you? So, so let us assign codes to the zones. So you got here, right? We can see that each symbol is having 3 bits, 000, 001, and so on. And now I am explaining to you quantization with examples. You have to listen carefully, and only if you understand, you will be capable of doing problems. Okay. Number of bits per sample will be 3 because the quantization level is 8. So we are assigning values to each of these sample points, midpoints, or the ranges. We have 8 ranges because 20 minus 20 by 20 minus -20 by 8. 40 by 8, you have 5 zones. So this is how you will quantize a signal with example. Okay, I'm explaining to you with an example. You need to understand this very clearly. So here I have graphically represented these values here. We have 8 quantization levels, 0 to 7. Each level you have 1 point, D, 2D, and so on. And each point is encoded with one particular set of symbols. Okay, if you look into this encoding system, you can easily understand how it is encoded. This is how a pure sinusoidal signal with maximum value 20, that is 4D to minus 4D, is quantized. This would be the output of the quantizer. You get this encoded words from 0102 010 or whatever it is, like this. Next, we'll find out the quantization error for these values. What is quantization error? When you quantize, you are not getting the exact value. You are taking some midpoint, and from there is a deviation. So that deviation will be a distortion, and the distortion is called as quantization error. Okay. So when a signal is quantized, we are introducing a kind of error. The coded signal is an approximate of the actual amplitude value. The difference between the actual and the coded value is called as the quantization error. The smaller the step size, the lesser the errors. When you increase the step size or the number of quantization levels are less, what happens? There is more gap, no? So there will be more error. Obviously, you have more gap, more error. So it is always better to have more number of quantization levels to improve accuracy. At the same time, we have to optimize it in such a way that the values are not redundant and there is no, sometimes if the levels are so high, it loses the purpose of digitizing the signal as a whole. So we have to have those considerations also when we start quantizing or when we decide to make out the quantization mechanism. So signal to quantization noise ratio. We have introduced another term called as signal to quantization noise ratio, SNQR. We have seen that most of our audio or voice signals are having very low amplitude, and in most cases we'll be working with low amplitude signals. So what happens is that the quantization error becomes large because we have a different variation from in terms of amplitude. Certain times you have very low amplitude, certain times you have no signal at all coming. So what we can do is that we need to, if the quantization is uniform, what happens is that we cannot have a common or a standard signal to quantization noise ratio or something like that. So we go adopt non-uniform quantization for that in such a way that we have smaller step sizes at lower amplitude, and at higher amplitudes we have larger step size. So what we have decided is that we will be changing the value of delta according to our need. We will make delta in such a way that it is flexible. This approach is called as non-uniform quantization. Okay, so we can do this by companding also, by compressing and expanding at the, that's what we have seen in the previous classes also, right? For voice signals, lower amplitude signals. Next is a very important topic. We are going to define bit rates and bandwidth requirements for pulse code modulation. What is bit rate? The bit rate of a PCM signal is calculated by the number of bits per sample into the sampling rate, Fs. The bandwidth required to transmit this signal depends upon the type of line encoding used. You can refer to our previous sessions for more details on this about bandwidth, because we have already dealt with that in the previous sessions. A digitized signal will always need more bandwidth than the original analog signal. So this is a very common mistake that people make, and we get this question very commonly in interviews. One of the biggest disadvantages of digitizing a signal is that it consumes more bandwidth. Listen carefully, all of you. So which kind of transmission is more bandwidth efficient, analog or digital? Nandana, tell me, which kind of transmission is more bandwidth efficient, analog or digital? Why? Analog is right, but why? Next is the PCM decoder. You all, thank you very much.